Let's get started with the Nearquad lesson. And I will run get your notes.
What's the Nearquad thing again?
Excuse me?
What is the Nearquad code again? YUVQT.
YUVQT. You all stated one. Anybody else? I gave it out. Yep. Still have to come by my office.
Okay.
Then actually, we really have already gone through the first part of this, but since several of you didn't have the handout, I'm going to assume you didn't have that part of it either. So we'll go ahead and start at the beginning. We're still talking about probability.
Is this a new handout?
It's one I gave out last time.
Okay. What's the code?
YUVQT. Looks like this. So this is probability distributions, which is just a table that contains the values of the random variable, which must be numerical, by the way, even though you can have a probability distribution that quantifies categorical variables. If we're going to talk about random variables that are numeric, then the probability distribution is going to have X representing a certain number of outcomes. So a random variable is a quantitative variable that assumes a value that is determined by chance or random outcome. And we usually represent it by X. Random variable is discrete if the number of possible outcomes is finite or countable. Basically, the way that you remember if it's discrete or continuous, if it's discrete, all you need is your brain and your hands to count. You don't need any measuring devices. You don't need any tools. You just count things that are discrete. That includes money, because the smallest quantifiable amount of money that we have in our money system is a penny. In other money systems, there are also a smallest denomination. So money will always have a smallest denomination, even though that denomination may result in a decimal being the answer. Don't take it that discrete means that it can't be a decimal. It can. But there has to be nothing between 0.01 and 0.02. A random variable is continuous if it can take on any value within an interval. The possible outcomes cannot be listed, and the continuous random variables are determined by a measure, and that's the key difference. In order to quantify a continuous random variable, you have to measure something. You have to have a yardstick, you have to have a scale, you have to have a ruler, you have to have a measuring cup, you have to have some kind of device to find its weight, its length, its height, the temperature, whatever. There has to be a measuring device if it's continuous. So here's 3 questions. X represents the number of players on a basketball team. Is that discrete or continuous? Because you count them, okay? X represents the length of time it takes to swim 4 laps in a pool. Discrete or continuous? Continuous, because you have to have a stopwatch. X represents the number of daffodils planted in a garden. Discrete, because you're going to count the flowers. X represents the height of 7th graders. Continuous, because you need some sort of a measuring device, a yardstick, a measuring tape, a meter stick, something like that. We're going to define a probability distribution. The first thing you do is you have to assign a probability to the random variable, either through experiment, through empirical study, through classical probability, or basically just observing how often it happens. So you assign the value. A probability distribution is a description that gives the probability for each value of the random variable, usually expressed in the format of a graph, table, or formula. So we're going to actually look at all 3. So a probability distribution can be a table that shows the different values of the random variable along with something that represents the probabilities, like a decimal number or a percentage or a fraction. But it can also be shown as a graph that looks like a histogram, where the heights of the bars will indicate things that are more or less likely.
Why are we distinguishing this from previous distributions that we looked at? I mean, there were probability distributions.
A relative frequency distribution is indeed a probability distribution. Okay? A frequency histogram isn't, because it's not about probabilities, and yet it'll probably still have the same shape. But a relative frequency distribution and a probability distribution are exactly the same thing. Okay? Now, we will also have a formula for one particular type of probability distribution that we're going to talk about. We're going to talk about something called a binomial probability distribution, and those probabilities can be determined by a formula, but the formula basically is a shortcut to having to actually work out every single possible outcome. So we'll talk about that in a few minutes. These are the requirements for a probability distribution. It's the same as the probability requirements that we had in Chapter 4. If you add up all the possible values of the probabilities, then that probability has to total up to 1 or 100%. And every individual value of X has to have a probability somewhere between 0 and 1 inclusive. 0 meaning that that particular value couldn't happen, and 1 meaning that that particular value was the only thing that could happen. Everything else would be somewhere in between. So here's an example of a probability distribution. Except for one thing. Add up the probabilities. Do they come up to 1?
No.
No. 0.10 plus 0.20 plus 0.30 plus 0.20 plus 0.10 is
0.9.
0.9, and that is not 1. Okay? So the probabilities do not equal 1. Is this a probability distribution?
It's over 1.
It adds up to more than 1?
I think it does.
Now the probabilities do add up to more than 1, so the answer is no. The sum of the probabilities is greater than 1. So now you have a question. There's going to be 2 of these. This is not a quiz question, it's just an open-ended question. You can type your answer. Is the pictured table a probability distribution? If not, why not? Okay. And that's the correct answer. No, because the probabilities added together do not equal 1. Okay? Now we'll talk about the mean and standard deviation of a probability distribution. They do in fact have a mean and a standard deviation. The mean is calculated exactly the same way that we would have calculated a weighted distribution or a weighted mean in Chapter 3. You would multiply the value of x times its probability and then add all those up. The mean is referred to as mu because it is the mean of a population. A probability distribution applies to the entire population. It's also referred to as the expectation or the expected value because it's what you expect to happen over time if you repeat the experiment many, many times. It's also what you might call the long-run average. So this is how you would find the mean and standard deviation of a probability distribution. To find the mean, you would multiply x times the p of x column, and then you would add up that third column. So 0 plus 0.0091 plus 0.1296 plus 0.6891 plus 1.6288 plus 1.4435 will give you the expected value of this distribution, which is 3.9001. And if you look at that number, that sort of makes sense because which one of the numbers, which one of the values of x had the highest probability?
4.
4, and 3.9 is very, very close to the 4. The only reason it didn't come out to be exactly 4 is because 3 and 5 also have relatively high probabilities compared to the other numbers. So those tempered that 4 a little bit. It's much easier to do this if you need to do the standard deviation on the calculator rather than trying to do it by hand. So you can get both the mean and the standard deviation by entering those numbers into your calculator, the x values in list 1 and the probabilities in list 2, and then calculate one variable statistics, being careful to specify that the statistics you're asking for are for the table, not just one of the lists. So you have to tell it the list that the x values are stored in and then the list that the probabilities are stored in with a comma between those two. And notice here it says x bar equals 3.9025, but in reality, and I think I may have misentered one of those values. Let me look. Grab my table with it, because that should have come up to be the same answer as before. We'll double check that. got a feeling that actually got entered as a 0, and that's what the problem is. Yes. I will correct this slide. There is your correct mean and standard deviation. So the mean is 3.9001, but you can't take your calculator's word for it that that is X bar, because it isn't. That's mu. That is the mean of the population. And the standard deviation, if you notice, you're not given a sample standard deviation at all, because this is not a sample, it's a population. All probability distributions represent populations. So your standard deviation is sigma, which is 0.92602375524, and it would be all right to round the standard deviation to 0.926. That would be fine. And you could round the mean to 3.9, and that would be fine also. Okay? So, are you ready to take the quiz?
Basically, for some reason, when I try to put both of the list in the bars thing, it didn't work.
Let's see. One of these two should have a 0. You don't have to read the whole thing. That's right. Yeah, I'm fine. Make sure when you do this, that's a good thing to make note of right now. When you do this, make sure your two lists have the same number of entries in them, because they are paired. So if one list is too short, the calculator is not going to give you the answer. It's going to fuss and tell you to go back and fix it. So what I've given you here is a probability distribution, and I'm asking you first, what is the expected value? And then second, I'm going to ask you for what the standard deviation is. Still waiting on some answers from some people. Sorry. So anybody that hasn't put their answers in yet, because it doesn't show up here as immediately as it should. Okay, this is not for a grade, so just checking to see where you are. Now, these are my answers, not yours. And mine were blank. The correct answers are in green. So the mean was mu equals 6, not x bar, mu. And the standard deviation was sigma equals 1.5837, not s. This was more a question of are you using the right symbols? This is a probability distribution. You have to be using the right symbols. Now we're going to talk about something called binomial probabilities. But I think we're going to take about a 10-minute break, 8 or 10-minute break, since you've been sitting there long enough for your brain to get a little tired, want to go to sleep. So get up, move around, get some oxygen, and we'll come back and talk about binomial probabilities. Okay, let's finish up and talk about binomial probabilities. Binomial probabilities are probabilities that are associated with something called a binomial or a Bernoulli experiment. Bernoulli was a mathematician and was famous for his research in probability theory. Binomial actually comes from two Latin words actually. Bi means two, and nomen in Latin means name. So binomial basically means two names. And the two names in binomial probability are success and failure. Not in any kind of an implied good or bad way. Success means only that the outcome that you're observing did occur. And failure means that the outcome that you're observing or counting did not occur. So it either happens or it doesn't. The features of a binomial experiment are, first of all, there has to be a fixed number of trials. For example, if you toss a coin 3 times, you want to toss it 3 times every time you do the experiment. That's a fixed number of trials. You don't toss it twice this time, and 5 times next time, and 1 time this time, and then the next time 3. You do the same number of tosses each time. And we're going to refer to that number of trials by the letter N, which you might associate with the number in your sample. And in fact, it actually is, in this particular case, it's the number of possible occurrences of success in the problem. Those trials have to be independent. You can't vigorously toss the coin and let it bounce around the first time and then just slam it down on the table the second time. That is not identical. You influence the probability the second time around. So they have to be independent. Births of children are independent. Just because the last child was a boy doesn't mean the next one's going to be a girl. And those trials also have to be repeated under identical conditions. As I said, you want to vigorously toss the coin. You want to mix up the number of the candies in the jar before you pick out one. You want to shake up the cookie jar a little bit to make sure they're mixed up before you pull out a cookie. But every trial can only have 2 outcomes. One is called success, which means that what you were counting was evident on that particular trial, or failure, which means what you were counting was not evident on that trial. For each individual trial, the probability of success has to remain the same. And that has to do with the fact that the trials are independent. We're going to call the probability of success P, and the probability of failure is going to be Q. And I would hope it makes sense to you that P plus Q must be 100% or 1, because either you succeed or you fail. There is no in between. So if you know P, you can find Q. If you know Q, you can find P. And the central problem we're looking at is how to find the probability of R successes out of N trials. And I know that all just sounded like a bunch of algebra gibberish, so we're going to go through and do an example. But here's a quick summary. You might want to make a note of this on your handout. This is a quick summary of what you need to have.
Can you go back 1 slide, Sarah?
Sure. Okay? So this last page will give you a way that you can fill in the bottom page of your notes. And I realize we skipped a couple examples. We'll go back over them for practice. So there's a fixed number of trials noted by N. The trials are independent and repeated under identical circumstances. Each trial has 2 outcomes. The outcomes are classified as success, denoted by S, or as a failure, denoted by F. The probability of success, P of S, is denoted by lowercase p, and the probability of failure is denoted by lowercase q, and then P plus Q has to equal 1. The random variable counts the number of successful trials. So X is going to be 0, 1, 2, 3, 4, up to N. And the central problem is to find the probability of R successes out of N trials. Okay? Now, this is a big, ugly formula, and you do not need to memorize it, nor will we use it every single time we do a problem. This is the formula that your calculator has stored in its memory under a key called distributions. And the only thing we'll have to do is be able to figure out what is N, what is R, and what is P. The calculator will do the rest. Your calculator does not have this formula. It will be given to you on the test. The only thing you need to remember is that the mean is n times p, and that's also called the expectation, and it is a mu, it is not x bar. It is a population mean, and the standard deviation is sigma, and this only works for binomial, where you would know n and p and q. If you multiply n times p times q and take the square root of it, it actually will give you the standard deviation without having to enter a table with all the values in it. So here's an example. A doctor tells you that 80% of the time a certain type of surgery is successful. If this surgery is performed 7 times, find the probability that exactly 6 surgeries will be successful. Now, success in this case means it fixed whatever the problem was. Failure means that it didn't fix whatever the problem was. The number of trials is going to be 7 because you're going to have this surgery performed 7 times. And it has to be performed under identical conditions, which means that it's the same operating room, the same operating crew, similar time of day, same exact surgery. So you're going to have to make some assumptions in some cases for binomials. So if this surgery is performed 7 times, what's the probability that 6 of those surgeries will be successful? Well, you would hope 7 of them will be successful. But 6 might be an acceptable outcome if it's not a life-threatening surgery. All we want to do right now is find n, p, q, and x. N is the number of trials. What's the value of n? 7. Okay, what's the value of p, the probability of success? 0.8 or 80%. And we'll have to use the decimal, so we'll actually refer to it as 0.8. What is q then? 0.2, because 20% of the time then you would have a failure. And what is x in this case?
6.
X is 6. It's the number of successes. Okay? Now, I went ahead and skipped over this part. We've already answered these. So we're going to let you skip over that too. I've already got my attendance from the other question. Now we're going to do the problem. Doctor tells you that 80% of the time a certain type of surgery is successful. The surgery is performed 7 times. The probability of exactly 6 surgeries being successful. Plugging into the formula. 7 factorial is the number of times you're going to perform the surgery, the number of trials. 7 factorial is defined as being 7 times 6 times 5 times 4 times 3 times 2 times 1. 7 minus 6 is the number of failures. So 7 minus 6 is 1, and 1 factorial is just 1. Yes, ma'am?
It kicked me out of there. What's that?
Y, U, V, Q, T. And then 6 is the number of successes, and that'll be 6 times 5 times 4 times 3 times 2 times 1. You can see where the arithmetic here would get very tedious. The probability of success is the 0.80, and if you have 6 successes and 1 failure, then that basically means that you're going to have 0.80 for the first success, 0.80 probability for the second one, 0.80 for the third one, 0.80 for the fourth one, and so forth until you get 6. But the last surgery would be a failure, so it would be 0.20, as you see here, and it's only raised to the first power. So we're using exponents to keep from having to write all this stuff out. Now let me tell you what each part of the formula does, so that you understand what the formula is actually doing. This is giving you the number of successes with their probabilities, and it's saying what's the probability of 6 successes. First success times second success times third times fourth and so forth. This is the probability of that 1 failure. And this is how you find the 1 failure. 7 minus 6 successes is 1 failure. What this part of the problem does What that first part does is it counts the number of different ways the successes and failures can occur. So actually this comes out to be 7. When you work out all the math, it comes out to be 7 because there are 7 different places in the outcomes of 7. There's 7 different places for the one single failure to occur. The failure could be the first one, it could be the last one, it could be the second one, it could be the fourth one, it could be the fifth one, it could be the third one, it could be the sixth one. It would occupy one place among those 7. So the 7 there actually counts the number of different places that your failures can occur. The number of different ways that one success and one failure and 6 successes can actually be arranged. So that's what that first part of the formula does. It's actually called the formula for combinations, and it does take order into account. And that probability, if you notice, the probability of 6 successes out of 7, even with each one having a high probability of success, the probability you have exactly 6 successes is 0.367, which is probably counterintuitive to most of us. You think, well, it should be a lot higher than that because there's an 80% chance of success. This is saying the probability of getting exactly 6 successes. Not at least 6, not at most 6, but exactly 6. So actually the probability of having exactly 5 successes would be pretty high also. And the probability of having all 7 be successful would be fairly high. So when you take all those into account, the one you want to worry about is what's the probability of having no successes? Okay? All failures. And we want that probability to be really small, and it would be. We could calculate that with the same formula. Binomial example number 2. Multiple choice test has 8 questions, each of which has 3 choices, and one of those choices is correct. You want to know the probability that you guess correctly on exactly 5 questions. Why 5? Because you passed the quiz. Okay? Find N, P, Q, and X. Read the problem carefully because I'm going to actually ask you to identify those. N is your number of trials. P is the probability of success, which would be the probability of guessing a correct answer. Q is the probability of failure. You guessed the wrong answer. And X is the number that you want to get right. Put your answers in separated by a comma in order, N, P, Q, and X. take it up at the second test.
Okay.
Okay, the correct answer, n is equal to 8, because there's 8 questions. P is equal to 1/3, because there's 1 out of 3 correct answers. Q is equal to 2/3, because there are 2 incorrect answers out of 3. And you want to guess 5 questions correctly. Plugged into the formula, your probability of getting exactly 5 questions correct is 0.068. Not too good. But remember, that's exactly 5. Not 5 or more, just exactly 5.
Miss Hunt,
Yes?
at the bottom of the page, is that how you do it in the calculator?
Yes. And we're going to do that too. Now, we can work this problem. We can work this problem using the calculator rather than that formula. All you have to do is you first press your distributions button. I'm going to get the calculator up here and show you where that is. You press the second button first, the one that says second on it, and then you press the bars key. So second and bars get you to the distributions. Then you'll scroll down until you find binomial. Now on the 84, it's not the same option as it is on the 83, but if you'll scroll and find it, it will still say binom PDF. Okay? So you go down and find that one and press enter. And then you need to put in the values of n, p, and x by reading the problem. It'll do the arithmetic, but you have to find the values of n, p, and x. Now here's a logic lesson for you. If there's 2 numbers, n has to be the bigger one. You can't have 8 successes out of 5 trials. Okay? You can only have 5 successes out of 8 trials, or 4 successes out of 8. So n's got to be the big one. It has to come first. P is the probability of success. The last number is the number of successes that you're looking for. So in our case, we had 8 questions. And the probability of success was 1/3, and you can put in fractions. You don't have to change it to decimals. And then you want to put in the number of successes, which is 5. And you always want to close your parentheses because you want it closed where you want them closed, not where the calculator decides to close them. And then you hit enter. And if you were doing the problem by hand, you don't even have the formula filled out by the time it comes up with the answer. But that is the exact same answer that we got before. Okay? That is by far the preferred method for doing this problem. Now suppose, and this is not part of the presentation, Suppose that I wanted to know more about those probabilities than just getting exactly 5. Well, I could do that. I can actually make a probability distribution table using this formula. So we're going to keep the same information you have in front of you, but I want you to get your calculator. I'm going to clear the home screen and we're going to hit Stat. And then enter to edit. And if you'll follow the directions along with me at the bottom of that same page, it says for accumulated probabilities, the formula can be used on the data lists on the screen to find probabilities for a range of x values, such as the probability x is less than 3 or equal to or greater than 5, or between 2 and 6. So enter the required x values into list 1. List 1 is how many successes could you potentially have out of your 8 questions. How many could you guess correctly? Well, you could guess 8, but you also could guess none, right?
Yeah.
So 0, 1, 2, 3, 4, 5, 6, 7, or 8. Okay? And for each of those values, there is a separate probability, which you could get by entering the probability distribution formula in each one of these cells and do it 8 times. Well, 9 times because you have to include 0. But it's faster if you'll do what I'm about to show you. It says put your cursor on top of list 2. Please highlight, draw a circle around, put big stars on top of list 2. Not at the top entry. On top of L2. Right there. It has to be actually sitting on top of and highlighting L2. This is similar to the way that Excel does formulas. You can actually do a formula in a cell, or you can copy a formula through several cells. But in the calculator, you can actually get it to go ahead and do the copy all at one time. So you go on top of list 2. Then you press second vars. You get your distributions menu. You scroll down. If you get binomial PDF, and you hit enter. And it copies the formula in there for you, and it's waiting for you to tell it what is in, what is P, and what is X. Yes, ma'am.
I don't have L2. I don't know.
Did you delete it?
I
accidentally?
Probably.
Okay. Hit your stat button.
Okay.
Go down to number 5, setup editor.
Okay.
Hit enter. L2's back in there.
Okay. Oh, okay.
Okay, now what I want it to do is I want it to calculate that binomial formula for this whole list. What's the value of n? 8. And we need a comma. What's the probability of guessing correctly? 1 divided by 3. And we need another comma. Where are the x's? Where are the values of x? In list 1. Second, and the number 1. Close the parentheses.
How do you close the parentheses?
There's a button on the calculator right above the number 9.
This one.
Oh,
Yes.
What in the not since you're including zeros?
Because there's only 8 trials. 0 is a possible value for 8 trials. Okay, remember it starts at 0 and goes up to the end. Now, does everybody know what we've done so far?
How did you get your L1 again?
Second and the number 1.
I mean, like the total value, like how many numbers are enrolled? Would it be 8 because it's 8?
There's actually, it is, you want the numbers that are in L1. Put the cursor on top of L2. Second, bars. Okay. And you have 8 trials. And your X values are in list 2. Okay, so second. What do you mean? Because the most number of successes you can have would be 8. Okay?
That's right.
Right, because all the numbers for X are in list 1.
Okay, so we'll put in
Second
So
cars.
I missed it.
No, second and bars. Okay, now scroll down and find your binomial. There you go. Get down there. Now, you have 8 trials, so you put in the 8
So that's
in the column, and it won't work on the keyboard. Well, I've had to learn that over the years. The probability is 1/3 for a correct answer. And then another column. And your X values are in list 1. Second and the number 1. You have to be sitting on the top.
Oh, yeah. Close it.
Yes. And hit up.
Okay, thank you.
Can you help her?
Yes.
Anybody else need help?
Okay. Second one.
Well,
And then what's the end?
enter next.
It doesn't. Oh, you just got a parenthesis there.
What would you get?
It here. And you put it on top of that list. Right there. And then now here you go. 8, comma, 1/3, comma.
okay. You don't want. No, you don't want 5. You want all the numbers that are in list 1, so you want list 1. I'm asking you to do the formula 9 times. Each one of those values is the X.
So you put
Second and 1 for L1. Now you close your parentheses. Yeah, a very short amount of time when you consider it did that formula 9 times. Everybody else okay? Anybody still stuck? I haven't hit enter yet. I was waiting to make sure. Now, here's the key things that can go wrong. You must be on top of L2. You cannot be sitting right there. You have to be sitting on the name of the list, because that way it recognizes what you want it to do. And when you hit enter, what it's going to do is it's going to run get that binomial formula. It's going to plug in n equals 8 and p equals 1/3 and 0 and calculate an answer. And then it's going to go back and do it again. Well, it's going to let the x value be 1. Then it's going to do it again and let the x be 2. And then it's going to do it again and let the x be 3. So it's going to go down all those numbers in list 1, and it's going to give you the entire table in less time than it takes you to copy down the formula once. Okay? Let's talk about what these probabilities mean, because that's the important thing. There is about a 3.9% chance that you're not going to get any of them right. There's a 15.6% chance that you're only going to get one of them right. There's a 27.3% chance that you're going to get 2 or 3 of them right. In fact, if I were to ask you what the expectation is here, it would be somewhere between 2 and 3. I would expect to get 2 or 3 right. They have the highest probabilities. The probability that you get all 8 right is, for all intents and purposes, 0. Because that E-4 says you have to move this decimal 4 places in front of the 1. So that's 0.00015. So 1/100 of a percent chance. Not very likely. You're also not likely to get 7 of them correct. You've only got about a 0.2% of getting 7 of them correct. You do have a 1.7% chance of getting 6 of them correct. So let's talk about what you really want to do. What do you really want to do? You want to get them all right, okay? Well, there's your probability you get them all right.
If you guess.
If you guess, totally guess, not an educated guess, just, randomly guess.
Wouldn't wind up being a very high GPA.
No, it would not. Does 5 out of 8 let you pass the test?
Grading scale are we going by?
The standard 65% is passing. Does 5/8 let you pass?
Don't have much of a percent.
By not too high a percentage, but yeah, you pass. Okay? So you need to get at least 5 correct to pass. Is that right? How many is at least 5?
0.08794.
So 5 will pass you, 6 will pass you, 7 will let you pass, and 8 will let you pass. So if I wanted to know what's the probability that I pass the test,
Five would be greater than or equal to 5.
I want it to be greater than or equal to 5. And those probabilities would be 0.06828 plus 0.01707 plus 0.00244 plus 0.00015. And I would have to add those up. So I have about an 8.8% chance of passing. What does that tell you about whether you better study? And that's if there's only 3 options. If you increase it to 4, that drops dramatically.
I mean, you can usually rule one out.
Usually, but this is just randomly guessing. Yes, you're right. You can improve your odds substantially still by studying, so you can figure out which one to eliminate.
Yeah.
Okay?
I keep thinking of the Dirty Harry quote.
You feel lucky. Yeah. probably shouldn't feel lucky if you're guessing on a multiple choice quiz. Now, true, false, you got a little better possibility. A little bit better possibility of passing, but not with multiple choice. So the next time you say, I want a multiple choice test, think about that. You probably really don't. Okay, we've got about 10 minutes left. Let's skip back in the handout and do some examples. I'm going to start off with example 1 and 2, which are from the first part of it. And this should prepare you to be able to do some homework and come back with questions if you have them on Monday. So example 1 gives us a probability distribution along with the graph of the probability distribution. So you could use either one of these to answer the questions. It says a survey asks a sample of families how many televisions are in their household. Is this a discrete probability distribution? Well, question number 1 on is this a discrete probability distribution, are your X values counts? And if so, what's it counting? What does 0, 1, 2, 3, 4 represent?
The number of televisions.
The number of televisions in the household, and they are counted, so yes, they are discrete because they are counts. Are all the probabilities between 0 and 1? Yes. And here's the final question. Do the probabilities add up to 1?
Yes.
Yes, they do. So I want to know the expected value, the standard deviation, and the variance. Now, before I even calculate the expected value, I'm going to point out to you that I should get a number somewhere between 2 and 3, because those two have the highest probability. The way that I'm going to calculate them is I'm going to use the calculator, because this is not a binomial distribution. It's not binomial because they didn't say, do you have television in your household, yes or no? So there's more than one potential outcome. So we're going to go to Stat, Edit, and I'm going to clear out List 2 because it's longer than I need. And List 1, I've got 0, 1, 2, 3, 4, so I can just delete 5, 6, and 7, and 8, and go over into the probabilities in List 2. And then Stat, Calc, 1 bar stats, X values in List 1, probabilities in List 2, and the expectation is 2.17. So we would expect any one given household to have 2.17 televisions. Yes?
Can I see what you put in the calc
You want to see the command or what's in the list?
No, what's in the list?
It's the same as this table. Okay?
I'll put it on.
Are you getting a different answer?
I got 2.5.
Oh, I see it. That used to be a two, but I'll fix it. Okay. So the meaning of the expectation is, in English, we would expect any given household to have 2.17 televisions. Now, in truth, can a house have 2.17 televisions? No. So what does that really tell you? Most of the time it'd be 2, they might have 3. Okay? Does that make sense? Most of the time it's going to be 2, but they might have 3. That wouldn't be unreasonable. Now we want to talk about the standard deviation in this case. The standard deviation is 1.158. And what that tells us, as we'll learn in a future chapter, is that about 2/3 of the time, a household, and let me get that down out of the way, will have 2.17 plus or minus 1.158 televisions. In other words, 2 plus or minus 1. It would be relatively common to have 1, 2, or 3 televisions. Right? That lets you put a little more common sense values in there. It wouldn't be extremely uncommon for them to have 4 because obviously 13% of the households do. So it's not extremely uncommon, but it's much more likely that they're going to have 1, 2, or 3. Now the variance, you simply take this number and square it, but don't round it off first. So the variance is 1.341 and tells us absolutely nothing. The standard deviation symbol is sigma. The variance's symbol is sigma squared. Okay? Be sure you get your symbols correct. Questions? Example 2. We again have a probability distribution. This time it's talking about the number of peas with green pods among 8 offspring peas. This is called a Mendelian experiment. It's a biology experiment. Has to do with genetics. So we could have none, 1, 2, 3, 4, 5, 6, 7, or 8 green peas. And their probabilities, when it says 0 plus, we're going to just figure that's as close as we can get to 0. And as far as the question of whether or not that's a probability distribution, it is a discrete probability distribution because these are counts. All the probabilities are between 0 and 1, and the last requirement would be that the sum of the probabilities is 1. And I can find that by hitting second stat, go over to math, and choose number 5, sum, and ask it to add up list 2 for me. And it says, yeah, that's 1. So yes, it is a discrete probability distribution. It meets all the requirements. Expected value, standard deviation, and variance. I hit stat, go over to calc, choose 1 bar stats, list 1 for the x's, list 2 for the probabilities. And it says the expected value is 6. So if we plant 8 plants, and they have each, or if we have 8 plants and we're counting the number of offspring that have green pods, then we would expect 6 of them to have green pods. The standard deviation is 1.222. Which tells us about how much that varies. And then if we square that, it's 1.494. So the variance is sigma squared, standard deviation is sigma. And this is E of x, but it's also referred to as mu. And then it says use the range rule of thumb to identify a range of values containing the usual number of p's. Something that we wouldn't be surprised by. The range rule of thumb says that you take the mean plus or minus 2 times the standard deviation, and that 95% of your result should be on that interval, which means that anything outside that interval occurs less than 5% of the time and would be very unusual. So if we take 6 plus or minus 2 times 1.222, our interval is 3.556 to 8.444. Now what does that mean in practical terms? Well, in the first place, we can't get 8.4. Most we get is 8. We don't expect to get less than 3.5. So 95% of the time we expect these values. And by that logic, would it be unusual to get 3? Yes. Based on the result, is it unusual to get only 1? Yes. One is not within the interval. Find the probability of getting exactly 7. From the table, probability of getting exactly 7 is 0.267. Find the probability, sorry about that, probability of getting 7 or more. That means I would have to add the probability of 7 and the probability of 8. So that would be 0.367. And then the probability of getting less than 4 is the probability of 0, which is 0, probability of 1, which is 0, plus the probability of 2, which is 0.004, plus the probability of 3, which is 0.023. So we'll just add those together. Okay? Now we've only got a couple of minutes left. For homework, I want you to go ahead and start working on your Chapter 5 homework in Stat Lab. If you checked your email, we have a test coming up next week. Week from today. That'll give us a chance to actually review a little bit before you actually take the test. But all your homework and quizzes, and Chapter 1 through 3 quizzes are open again now as well. So you can go back and redo Chapter 1 through 3 quizzes. And there will be probably about a third Chapter 1, 2, and 3, and then the other 2/3 will be Chapter 4 and 5 on the test. Okay? We'll continue working on the binomial next class.